Hello and welcome back to Calculus 2, section 8.4, divergence test, integral test, and P-series. We talked about sequences first. We said that was just a list of numbers, ordered list of numbers. And we only had one test, which was the limit test. You take the limit of the sequence, it either converge or diverge, and you're done. And then we ventured in the world of series, where the series is the sum of the sequence. So what used to be 1, 2, 3, 4, going on maybe to infinity, it becomes now the 1 plus 2 plus 3 plus 4 and so on. So for this type of series, if they're infinite, they can converge or diverge. If they converge to a sum, and if they diverge to infinity, which means they add to infinity, the members of the sum. Now, we covered geometric series and telescoping series. Those two are the ones that, if they converge, we know what the sum is. And that's why they're grouped in the first section, right? 8.3 took care of those two series. What's left is another 8. So 3 today, and the rest on Wednesday. And those 8 that we study this week, we don't know what they converge to in sum. We would know if they converge, if they diverge, but we will not be able to calculate the sum. And we start with the divergence. We start with the divergence test, which is a very powerful test. And this one is interesting because, first, observe the title of it, divergence test. So it is designed to show divergence. Can it show convergence? No, because the title is divergence test. All right? You can't tell someone that it's skinny because it's fat. Makes no sense. All right? So what you do is you are going to learn the theorem again, and then this will be your go-to first thing to try anytime you see a series. Remember how your U sub is a thing to do? Like if you flip your last exam to the last problem, right? To the last page, the one that I switched in the last second, right? Do we see a little smiley face there? Yeah, it's a U sub problem. Now, how many do we have working on a trig sub there? Yeah, I know, almost everyone. It's a U sub. Yeah. Problem number 9 is a U sub. It was improper, so it's Calc 2, right? It's improper type 2, but it's a U sub problem. So you should do it with a U sub. U sub is this go-to technique, right, for integration. Chain rule is the one for derivatives. So most of the time it's chain rule, most of the time it's U sub, and then now we have the divergence test. It's the first test to try on every series you ever see. Eventually you might have a test on this, right? Exam 3, if you want to have it. You are going to have on that test maybe 10, 12 of these series to test. The first thing you're going to do is you are going to take this divergence test and run against every single problem, because that one detects divergence. It might knock out 1, 2, 3 problems out of the whole exam. Same thing for the final. So you always have those, the first thing you try within derivatives, within integrals, and now within series, it will be divergence test. So now, what is this divergence test? How does it work? And so on. Let's see. All right. So, divergence test theorem. So, theorem says if limit of an as n goes to infinity is different than 0, then summation of an diverges from whatever to infinity, right? You can put any number here, 1, 0, doesn't matter what it is, whatever. So I leave it empty because it can be anything. Remember that for geometric series you must be at 0, right? Telescoping can be anything. So geometric series are very sensitive where you start because the sum changes the a. For the rest, it doesn't matter. So in general, I leave that empty because it could start at 0, 1, 2, or 10 million. It doesn't matter. So this is it, guys. That's it. So divergence test simply says that if you have a series. Remember, series is the sum of the sequence. Sequence is that formula that you have in a series, right? It says if the sequence within the series, if the limit of that is different than 0, then the series diverges. So what you might have is, right, you can have summation of n, right? When you send n to infinity, you get infinity. That's not 0, so you immediately say it diverges. So summation of n would diverge. We'll take a look at some of these examples. But I have another sentence still in red. Otherwise, test is inconclusive. This word inconclusive is very important here. It is very important for you now to know that this test cannot be used to show convergence under any circumstances. This test cannot show convergence. And please think before you write something ridiculous like convergence by divergence test. Think, right? Words. Yes?
So if you give an example, or if you get a problem that fails the divergence test, it still has a probability of being divergent, just getting...
Yes, just this test didn't work on it.
Okay.
Yes. So, examples. So we said summation of n going from, let's say, 1 to infinity. Well, we extract that an is n. That's the formula for the sequence within the series. Remember, series is the sum of the sequence. So now we have this n. And if you send limit n goes to infinity of n, you get infinity. That's different than 0. So diverges. If you go with the summation of 2 to the n from 0 to infinity. That's geometric, right? We know that this diverges by geometric series because r is bigger than 1. We did that last class. However, we also know that an is 2 to the n, and that the limit 2 to the n as n goes to infinity is infinity. Therefore, we have divergence of summation 2 to the n. Divergence of summation n. So we are able to look, this is extremely rare, we are able to look at a sequence and conclude something about series. That's a very dangerous territory. And tonight we're going to see why we need to retire the common sense and things and just follow mathematics, follow the rules, and memorize these things so we can use them, these theorems. So let's take a look at summation k over 1 plus k from 0 to infinity. So we extract ak as k over 1 plus k, and the limit as k goes to infinity is k over 1 plus k, which is what? One. Yeah. We have k over k, right? Front coefficients are 1 and 1. The highest exponent and the numerator is 1 and the denominator is 1, the same exponents in a polynomial setting, right? So you use the front coefficients, 1 divided by 1 is 1. So since the limit is 1, we have divergence of summation k over 1 plus k, because it's not 0. Right? That's what our theorem says. If the limit is different than 0, it definitely diverges. Oh, let's talk about the evil one. 1 over n from 1 to infinity. So an on this one is 1 over n. What's the limit as n goes to infinity of 1 over n? 0. Right? 1 divided by infinity, 0. Jacob, let's go. The what? Test is inconclusive. Very good. Test is inconclusive. You know what the answer actually is? Diverges. It diverges. Very good. Harmonic series. People do class preps. Very good. Very good. So yeah, this diverges. This diverges, but we are going to use a different test that show. So equal to 0. All I can say from here is that div test is inconclusive. That's the best I can do. I can't claim anything. So if the limit is different than 0, it diverges. If the limit is equal to 0, all bets are off. The test is inconclusive. We have to use something else. And that's the end of the story for this particular. That's the end of the story for this particular test. Yes.
So test is inconclusive now. You have to try something.
Yes, you have to try something else. So that's exactly what's going to happen on the exam. If you have 10 questions that are series, right? You will apply this test on every single problem. And probably 8 or 9 out of 10 will be equal to 0, which means inconclusive. Number of those will converge, and number of those will diverge. And this particular method will detect 1 or 2 in the entire exam that will be different than 0 in the limit, and you can claim divergence immediately. All right. Ready? Lock the doors. Integral test. There is a correspondence between our discrete world of n's and the continuous world of x's. What is that correspondence? Well, correspondence would be a function y equals x, which graphs as the 45-degree line going from negative infinity to positive infinity in its domain. And then what you do is you say, well, if I restrict the domain, on 0 to infinity, you get to draw just the first quadrant, right? So this line here is f of x equals x, y equals x. And then you have your discrete world where your an equals n. And that one graphs as a series of dots at 45. This is n, and this is an. So there is this correspondence, right? And the interesting thing is that anytime you graph any an, if you replace n with x, x will just go through all of those points. So now that we understand that there is this correspondence between the an world and the y world, f of x world, we can talk about the integral test. Because remember, integrals cannot, well, the integrals that we know of, the Riemann integrals, right? They cannot work on dots. You integrate from 3 to 7, and you have to have the line 3 to 7 so it boxes off the area, right? In this case, you don't have that. There is something later on in mathematics, Lebesgue integration and stuff like that. If you're interested, and you will run into those scary stuff, where you can integrate discrete points. But in what we are concerned here in calculus, throughout 4-year, right, education, integration has to be done on a continuous line. So, in order for us to consider integral test, we have to work out the conditions first, and then if the conditions are satisfied, we get to do integral test, and then we have the theorem which says whatever integral did, series will do the same. Because we're going to all right, well, let's see first the conversion. So say I have summation of 1 over n from 1 to infinity. From here, I can extract that an is equal to 1 over n. And then from there, I get that f of x is 1 over x. Now note that this n is not 0, it's 1, 2, 3, 4, going on forever. And over here, the domain starts at 1 and goes to infinity. So domain has to be the same, right? Starting from the same value. Our summation started at 1. Our domain for the function must start at 1. 1, 2, 3, 4, 5, 6 going to infinity. Well, our domain for the function is 1 to infinity. 1 included, infinity obviously not included. So we are keeping the same shape of the function, and we are starting the domain at the same number, and we are ending the domain obviously at infinity because this feature is always there. So technically, guys, you have your 1 and you have your infinity to create your interval for integration every time, which is your domain over which you're integrating. That's what it is. So that's a conversion between the discrete function sequence, right, and our continuous analog, which is in this case f of x equals 1 over x. which is continuous function on the interval. And now we can finally write the integral test theorem. This is where the pink box comes in. Integral test. It's a theorem. So we say if f of x is, number one, continuous, 2, positive, 3, decreasing, then the integral of f of x dx from, I'll put 0 to infinity. Actually, I don't want to put 0. I want to put some value there. Let's use value. Let's use, should I use b? Let's use b. Then, all right, and summation b to infinity of an both either converge or diverge. So what this means is that if the three conditions are fulfilled, then the integral and the series have the same fate. All right? That means that if the integral converges, series will converge. If integral diverges, the series diverges. So we don't compute anything with a series. We look at a series, extract the function, and that's it. The rest is all three proofs to show that these three conditions hold. Then feed the function into the integral, crank in proper integral, do the limits and everything else. And then whatever happens with that integral, the series will have the same fate. If the integral converges, series converges. If the integral diverges, series diverges. Here's our box for integral test. And let's do the first example. Start a new page in the notebook, right? So you can see the example in its entirety. You don't want to start halfway and then can't fit the problem. I guess the truth, right? So let's see what is happening with this summation 1 over n, 1 to infinity, right? Does it converge or diverge? We start by writing the continuous analog 1 over x, and we know that we are on the domain 1 to infinity because the series was 1 to infinity. Yeah. Now we have to do three proofs. Proof number one is if this particular function is continuous. And we only care about function being continuous on a domain that we have. We all know that 1 over x is not continuous globally, right? It has a vertical asymptote at 0. But we don't care about that part because our domain is 1 to infinity. Is it continuous on 1 to infinity? Yes, it is, right? So this is where your knowledge of functions kicks in. Sometimes you will have to do the proof. Sometimes you will just draw pretty pictures and you're done. So, conditions. Number one, is it continuous? Right? You ask yourself. You can draw a pretty picture because this is easy. right, function. And then you will say that this is where 1 is. And since you are only considering this part of the function, right, so you will write a sentence there. 1 over x is continuous on 1 to infinity. And you can see that on the graph. So that was a pretty easy part. The next one is it positive? Graphically, positive means is it always above x-axis? And you look at it and you see it is, so yes. And then you also can do the proof. Now, since you might be a little bit shaky on those proofs, I am going to do the proof. So here's what we have. Consider f of x 1 over x on 1 to infinity domain, on the domain one to infinity. Note that the domain contains positive numbers. Since 1 is positive and x is positive, the quotient 1 over x is always positive. And this is the proof. It simply says we are considering the function 1 over x on the domain 1 to infinity. Now you see a division. You know that positive divided by positive is always positive, right? Well, the numbers that you can plug in for x are only positive numbers. You can plug in pi, you can plug in pi squared, you can plug in 103, right? All of those numbers are in here. No matter which number you pick, you will always have positive divided by positive, and the quotient is positive. So the condition for positive is fulfilled as well. So we see that number 2 holds, and now number 3 decreasing. Is it decreasing? Well, yeah, that chemistry experiment didn't go too well. Take some and stop doing chemistry in math class. Take the whole thing.
That's all good, man. I got it.
Ah. Yeah, till you get there and see that that is not absorbent at all. And then... Oh, is it good? All right. All right, so we have, is it decreasing? Maybe I should spell it out because it looks like it's December. Yeah, is it December yet? No, we have another few weeks. This is decreasing. Well, there are 2 ways to show decreasing. One way is algebra way, and you can use the sequence for this one. You can show that the next term is always smaller, right? Because that means to be decreasing. The next number is always smaller. Or you can use calculus derivative. And if you always have a negative derivative, that means it's, right? Because negative derivative means decreasing. So I'm going to use derivative. We use the derivative. So now you have to wash the carpet.
Yeah.
So f prime of x is negative 1 over x squared. That's the derivative. And we are still on the same domain 1 to infinity. That doesn't change. Now, what do you see? Do you see negative divided by positive at all times? Right? So, since x is always positive, right? I'll point up there into the domain. The quotient negative 1 over x squared is always negative, which obviously means that f of x is decreasing.
Quick question.
On 1 to infinity. And there you go. This is it. We have all three. What's the question?
I missed the point. Why is it negative 1 all of a sudden? It's positive 1 over x.
The derivative.
So then I think the derivative of x minus 1 minus 1. We can take the 1 over x and make it x plus 1.
Yes. So minus 1 drops. Minus 1 minus 1 is minus 2.
And then drop the x down to x.
Okay.
That's 1.
All right.
So
We are done with conditions. We can finally set up the integral.
hold on. So then for number 3, you're saying I always take the derivative every time?
Unless you want to do the series, we'll sequence. We'll switch. We are ready now to set up the integral. Integral from 1 to infinity of 1 over x dx is equal to the limit b goes to infinity, integral 1 to b of 1 over x dx. It's improper integral, so we have to involve this limit. So limit b goes to infinity, and then what do you have? You have the, what is the integral of 1 over x dx? No. ln absolute value of x. Very good. From 1 to b, which is the limit b goes to infinity. And then we have ln b minus ln 1, which is 0, right? And now, what is the limit as b goes to infinity? Infinity. If you guys think of the ln graph like this, going through 1, as x goes to positive infinity, y goes to positive infinity. All right, we are ready to finally write the answer. Since 3 conditions hold and integral 1 to infinity 1 over x dx diverges, the series summation 1 to infinity 1 over n diverges by integral test. This is your answer. This is the sentence that gives you 2 points. And the stuff before, partial credit. This sentence says that you know the definition, right? The theorem for integral test. Because the 3 conditions hold, you can establish the correspondence between an and f of x, and then the correspondence between the integral and the series. Now, because the integral diverged, the series diverges as well. Cool, right? All right. Next page, next example. Summation oh, by the way, let me, before I do the summation, no, before I do the next example, I just want to give a name. So summation of 1 over n, which is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus ... forever, which actually diverges, is called harmonic series. That's the name. And maybe you want to memorize that one. Well, just, you know, 1 over n diverges in for series. So series of 1 over n diverges. Yes?
Didn't on the test you gave us the harmonic series, we could say that because we know the harmonic series diverges?
Yes, and you will be using that later in the comparison tests. Yes?
There's the old music was again 1 for n. And then kept adding. So you plug in 1 for n, so you got 1 over 1.
And then 1 over 2 and 1 over 3, 1 over 4, right? Because the counter over here goes 1, 2, 3, 4, 5, 6 all the way to infinity. That's what the 3 dots are at the end. So the sum will diverge, and this specific one is called harmonic series, and you will use this in other tests, actually, within other tests. So this is one of those results that you might want to memorize, even though this is not a test, this is just a name. You know how you memorize that the derivative of the square root of x is 1 over 2 root x? That was not a rule. It was just the one that shows up all the time, and you just memorize it, right? So this is the series that will show up a lot, and you just want to memorize it real quick and be done with it. Good. Class to 10, 11, right? So we don't have to rush. Next example. There are some wonderful examples in your textbook, such as summation 1 to infinity of 1 divided by cube root of k plus 10. It's a cube root of well, we are going to create the continuous analog f of x 1 over cube root of x plus 10. And we are on the domain 1 to infinity, which will be the limits of our integral. We have 3 conditions, right? So condition number 1, continuous. Is it continuous?
Yeah.
Why?
Because it's from 1 to infinity, and then...
No asymptotes within the domain, okay. Well, let's talk about Calculus 1 now. At one point in time, there was a Calculus 1 class, and in that class, in chapter 2, there was a lecture on continuity. And in the lecture on continuity, we had this theorem. Functions which are polynomial, exponential, logarithmic, sine, and cosine, and absolute value functions are all continuous on their domain. And then there were more. This is a composite function. And the next theorem says that if you make composition of continuous functions, the resulting function is also continuous. These are the two theorems from Calculus 1. And now we get to use them in Calc 2. So now, when the question is posed if the function is continuous, I will say k plus 10 is polynomial, therefore continuous. Cube root of, x plus 10. Cube root of x is continuous as well. Function composition of two continuous functions is continuous. Right? Since cube root of x plus 10 cannot be 0, because negative 10 is not in the domain, the quotient 1 over cube root of x plus 10 is continuous. Welcome to Calc 2. So you build this argument. When you have multiple functions, you consider continuity of each one of those functions independently. You know that x plus 10 is a polynomial, therefore it's continuous. You know that the square root, cube root, whatever root, nth root, whatever number you have in that root, nth root of x is continuous. So you have polynomial is continuous and the nth root is continuous. Function composition, theorem from Calc 1. Function composition of two continuous functions is a continuous function. Therefore, the function composition, where you take this x plus 10 and you plug in the cube root, that means that the whole block, which is our denominator, is continuous. Now, number 1 is a constant function. That's continuous everywhere. So now you have a continuous function divided by continuous function. Now that's a scary situation, because the denominator could produce vertical asymptotes. But it only produces vertical asymptotes if it can be 0. But our domain prevents us from having that 0, because the only way you're going to get 0 in the denominator if x is negative 10. But negative 10 is not in our domain. So that's cool. So denominator cannot be 0. All of the functions that we considered, whether they're a constant or composition or whatever, are continuous. So the whole thing is continuous. And that's how I build these arguments. So you have to completely disassemble everything. That's continuous, this is continuous, that's continuous. The division is continuous as long as this cannot be 0. Oh, it can be 0 because the numbers that make it 0 are not here. If any of the rule fails, the whole thing explodes. Yes?
So say like number 1, like if it's positive, right? It's positive coefficient. Yeah, or no, it's continuous. Oh, then it's positive. Okay, then. So say one of them failed, like right away. What should I do?
You cannot use integral test.
Okay.
You are only allowed to use integral test if all 3 conditions hold. Okay. If one of them fails, look for another test. You can't use integral test. Yes?
So is this wording like exact, or you want something like around general lines?
Along the lines, yeah.
Exactly.
The more you use the words therefore, hence, and so on, the bigger the value is. You have to use the mathy words. Or if and only if, exactly. But definitely therefore, since, and those things. All right, guys, we got one of the 3. Let's go. Second one, positive, right?
Yes, positive.
How do we know?
Because the numerator is positive, therefore it's positive.
Because of the domain. Very good. So is it positive?
Yes.
And you guys say yes.
Yes.
So So x plus 10 is larger than 0 since x is larger than 0, right? You know x is 1 and more. And then, I mean, the cube, there is another thing that you can do in this proof where you can say that the cube root function is increasing function, therefore when you plug this in it remains positive. But cube root of positive number is a positive number, and finally the quotient, since 1 is positive, the quotient of two positive numbers is positive number. Done deal. Is it positive? Yes, it is. But I want to do this in another way. In purple.
Is this like easier?
I don't know. You will pick your favorite and use it. I'm going to give you all of the tools, and half of the classroom will probably go one way, the other half will go the other way. Whatever makes you happy. Now, we know that an is 1 over cube root of n plus 10. And we know that an plus 1, which is the next term, is 1 over cube root of n plus 1 plus 10. So the other way, instead of oh wait, this is the positive. Yeah, I'm thinking of the next one. Hold on. Hold on. Erase every... Oh, you use pens? Good. Yeah, I was decreasing. For decreasing, we use the derivative, and then the other way will be purple, where I compare the terms. So decreasing, we use the derivative. Our f of x is 1 over cube root of x plus 10, which can be written as x plus 10 raised to the negative 1/3. That's algebra. So now the derivative, f prime, is negative 1/3 times x plus 10 to the 2/3, right? And then times the derivative of the inside, which is 1, but no one cares. So the whole thing is negative 1/3 times, and I'm going to do this, cube root of x plus 10 squared. The argument goes like this. Since the squared quantity is always positive, the product will be the product no, negative 4/3. I integrated. Negative 4/3. This is going to be 1 over cube root of x plus 10 raised to the 4th power. There we go. It has to work the same way. Oh, come on, roots. There we go. Since Okay, let's go. Raising the value to the fourth exponent or power, to the fourth power. No. Yeah. Gives positive value. So raising a value to the fourth power gives positive value. And then, yes, the product of negative 1/3 and a positive value is a negative number. So we see that decreasing is there, right? So 1/3x plus 10 is decreasing. Now other way, finally. Anytime when you have the decreasing portion, you can use the sequence, original sequence an 1 over cube root of n plus 10. And then you can create an plus 1, which is the next term, as 1 over cube root of n plus 1 plus 10, which is actually n plus 11. So this part over here is the next term. Now, all we need to do is to show that an plus 1 is less than an. That's all I need to do. Because the decrease means that the next term needs to be less. So all I need to do is to plug these in with the less than symbol and make sure that mathematics of that holds. What do I have? On the left, I have 1 over cube root of n plus 11. And that should be less, I'm asking myself, 1 over cube root of n plus 10. Cross multiply both sides. We get cube root of n plus 10. Asking ourselves, is this less than cube root of n plus 11? Well, if you cube both sides, that will kill the cube roots. So you have n plus 10 less than n plus 11. Take away n on both sides, and you get 10 less than 11. Good. So we got a true statement. So we have to show that the next term is smaller than the previous term. The next term is smaller than the previous term. And we plug what their equations are, work out the math, we got the correct statement. Are you always going to get correct statement? No. Right? So now we see that decreasing part can be done through derivative on the continuous function, or you can do the comparison of the an and an plus 1, making sure that an plus 1 is smaller. And this takes care of the proofs. So now that we know that all three conditions hold, we can finally integrate, yes.
Are you gonna, on the test, are you gonna...
It just says on the test, use the integral test, and then there is a series there, and you have the full page, and then you can flip later.
Okay.
Yes. Oh, it's nothing. The stuff that it's coming up. I mean, we're still going to do 3 or 4 examples. You have to worry about one of the next courses where you get to do 1 or 2 examples per class. This is nothing. It's nothing. Yes?
So every answer ends in a divergence
Oh yeah, 50-50, exactly.
So Lewis, we got to put a question.
Yeah, but writing convergence, divergence is only 2 out of 10 points. The 8 points are the rest of the stuff. So you're definitely good. If you have 100% luck, you're good for 20 out of 100. At the 100% guess rate, you have 20 out of 100. Now you're gonna have 50% guess rate, so you're 10 out of 100. I mean, it's better than 0, right? Make sure it's tomorrow by 4:30. All right, we can finally do the integral. My pen died. I think my pen died. Yeah, my pen died. All right, set up the integral. My pen died, so now it's just you guys. That's it. Integrate the function. 1 over cube root. Let's go. I can't. Look, pen is not working. The what? Quadruple. 4a. Oh, no, I just need to reset. But you know, you guys got this. This is improper integral. You practiced for the previous exam. You got this. And I also have a full pack in my. I mean, not full. I have 4 batteries in my pack.
Even though the battery?
Yeah.
Yeah.
Yeah. You need it?
I want to see that's one that comes up on.
No, your pen is not working because it doesn't like you.
Like I literally thought it like broke.
Oh no.
And I was confused. Like, how does that work?
That's a AAA, right?
Writing with
It's a quadruple A.
Just want to see.
There might burn.
See if it works. Alright, so my battery was dead.
Your battery's dead, yeah. Or maybe if you just plug it in.
Plug it in what?
Plug in battery now, because maybe it might reconnect it.
Battery's dead.
We are on domain 1 to infinity, and we are supposed to integrate cube root of x plus. How do I integrate this? U sub. Oh yeah, look.
That's nice. I always feel so jealous. The flash with like gold.
Look.
I'll give you money here. How much you want this?
$17.
Was it right on?
I'm just
Well, I'll buy you one.
just get away. All right, so we have integral of u to the negative 1/3 du 1 to b, which is the limit. So now we have limit b goes to infinity, and then when we integrate, we get u, which is x plus 10, raised to the 2/3 divided by 2 and then 3 in front, from 1 to b. So now this is, we can kick 3/2 in front of the limit and then apply the limit to the rest. B goes to infinity. We have b plus 10 raised to 2/3 minus 11 to 2/3. And we see immediately infinity there because you are going to add infinity plus 10 and then square it, and so it's infinity. So we have divergence again. So since this guy diverges, we write our answer. Since three conditions hold, and integral 1 to infinity of dx over cube root of x plus 10 diverges, series summation 1 to infinity 1 over cube root of n plus 10 diverges by integral test. Step number 1, show all three conditions. Step number 2, compute the integral. Step number 3, write the answer. The red stuff is the one that is the answer to the question on convergence divergence. All right, so it's about a page per problem, but it's manageable. All right, so here's one for you guys. This is going to be all you, 100%. I'm not getting involved at all. Ready?
Every time that comes back.
Oh yeah, that's exactly yeah.
You can hear it on the screen.
Oh really?
Yeah, when you're at home listening. What is this? Oh crap.
Now this is all you guys. 100% go. Yeah, proof 1, 2, 3.
Give me like progress.
Zero. Oh yeah, you can. Oh my God. No, that's square.
I'm not.
This is a new page from scratch. So do you want this?
Yeah, it works. Thank you.
By the way, if your pen dies, because then what happened is, you see mine perfect, right?
Yeah.
Just walk in the store and say he's dead. Did you? You just gave me a new one? You just said it died. You just gave me a new pen. That was it.
It's pretty cool.
Yes. I walked in with the computer, the pen says he's dead. Yeah. I was
They don't really care at all there. Like,
20,
they're like,
20 minutes, 20 seconds. Oh, 20 minutes, 20 seconds. Was it?
What's the answer?
I will see the page.
I can do that later.
So you can literally just go on eBay and buy a sheet of content and then this is
He did not ask me the name, the receipt, nothing. I walked in because a student told me that she said she went into the store and she was confused because she went into the receipt and everything and gave her the and I decided to try, right? So I went to the store and I said, and the one guy said, those are always confused. And the guy said, you only want to have a baby. And it looks cooler than the original one. So, I light in the spot, and I swapped the battery. It worked right away, and I pulled off in 20 seconds.
It must be like a common effect.
But again, for them it's nothing. Yeah, but these pens, pen is like $40, but you already have the pen in the thing, and there's some of these around.
Yeah, I wanna
Can be $3,000. Can be, depending on how much you put in. My Surface Pro 3 runs Diablo, Counter-Strike. I have to even run. Work runs half. Yeah, the battery is 9 hours. 9 hours battery.
I imagine, so you run it at like a constant 60 FPS or is it fluctuating?
Yeah, I can't go as the rest, but go ahead, try even on a regular computer.
Well, I know definitely couldn't do anything on
I felt like
Yeah. Like what?
What?
You want to try it?
I just realized it works for mine.
Yeah, digitalized pen. You just go buy it. It's $40.
No, I'm keeping it. Oh,
I can't go and I say I lost the pen. I can say because they took the broken one. They took the broken one and gave me a new one.
so what's
I didn't walk in and say, yo, give me a pen.
What conditions have to be met? Just have to give them the time.
Yeah, you can't even say that. Yeah, but that's here, take this pen. Oh.
So I got a pen off of eBay for like $4. And then get a $40 one.
I'm gonna sell $40.
And then and I buy another 10 pens. And then you have the exponential function then, right?
Yeah.
You make $4,000?
Well, the thing is, they'd probably catch on. So you'd have to pay different ones.
But that's just the
Just
conversation.
stand outside the Apple like, yo, can you get in and get me a new notebook? Yeah. Or whatever. Microsoft Store, whatever.
Ooh, F.
Just a motto.
Whatever his grade was on the last test.
Yeah. They're both fruits, right?
Technically,
So,
technically,
not a food in the church.
the original Mike in the
Like
90s.
whatever his test grade was divided by
By 7.
Are all these work?
You done?
They all work.
it's convergent.
Can I just sketch it? Can't you just sketch it?
No, because the integral test just sees if it, yeah. The divergence test is the one that you can't solve.
Because the 1 over n squared f of x
So it converges to something. We don't know what that something is. We just know it converges. Well, I mean, you could find out with the. Oh no, you can't do geometric. No, they're not geometric. You can't find out what number that is.
This is what I got.
But you don't know what kind of convergence.
You don't know what it I just throw
Try to find out what a
as
convergence
the
is.
summation
No,
of
that this just tells you that the integral is 1. That's all. That's all it's telling you. Yeah, I'm pretty sure the series doesn't converge to 1. I mean,
When does it run?
the 1 over 1 is 1, so it can't converge to 1. Yeah, it can't converge to 1.
Oh yeah, that's what I did too. So I got negative 1 would be plus 1 over 1.
If you do 1 over 1 squared, you get 1. And 1 over 2 squared, you get 1 over 4. So that's 1 plus. It's not 1.
All right, I got another 5 minutes. Want to see those proofs and things? So.
What is it?
I just sketched it. Well, it's just L, not.
Yeah, 1 over n.
It's like 1 over something crazy. We go worse. It's finals. Yeah, it's good pizza.
Oh, dude, no, I'm getting a penne box of pasta with chicken and stuff. It's good.
I don't know for sure.
Did you stop the stream or did it die?
Probably died. I did not stop it.
Are you supposed to follow Stephanie?
I don't have any notifications that it stopped. It says live. Stream should be okay. Try refreshing your web page.
Hey, do you know what this means? What is my computer? What is the screen? What is the screen mean?
Oh, you need to get the
That's wireless.
Convergence to like.
oh, so wait, the ones that do that?
Yeah.
You can only do
Well,
that
yeah, I
by
mean,
fucking it.
practically it goes the way of obviously you can have your phone, but there's the Wi-Fi, you can't do Wi-Fi.
I just did one.
But if you
One
don't
divided by
turn that off,
square.
then you don't have Wi-Fi, you won't be able
One
to
divided by one square.
They what?
The one thing that pisses me off is that I register emoji. So whenever you type in I automatically change it to that weird like A and Y.
Yeah, I told him.
Oh, it's not gonna give it to infinity, I think. Actually, it might, yeah, it might do it.
Huh?
Probably the next one out. Yeah, I don't know.
I don't know how to do it,
What is it? I didn't say that.
I looked this up. No, it's a certain word. What's the name of my computer?
You name it.
All right. Let's take a look at this problem together. I already showed two problems with full proofs. So in this case, I am going to do my my graph. The graph for 1 over x squared, because I know it, looks like this. And we are on 1 to infinity. So we are talking about this part here. And this part is clearly continuous. And it's positive. And it's decreasing. So if you know the graph, you have instantly write all of the answers.
Will that be sufficient for you?
Well, for 1 over x, yes, for 1 over x squared, but I'm looking at the next one. It says 1 over k ln k squared. Yeah, good luck with the graph. You have no graph in calculator. So unless you're going to crank a page in Calc 1 to graph the function, remember? So pick your poison, right?
Yeah.
So sure, easy on this one, easy on 1 over x, but not easy on 90% of the problems they have in the text.
Yeah.
So I have all three of these to hold, and I have the integral 1 to infinity 1 over x squared dx, which is limit x goes to b, b goes to infinity, integral 1 to b x negative 2 dx, which is limit b goes to infinity. The integral on x is negative 1 over x from 1 to b, and we are getting negative 1, limit, yes, points off, limit b goes to infinity, negative 1 over b plus 1 over 1. Now this guy goes to 0, and we have a convergence. Now, please notice that we got then answer 1. That answer has nothing to do with the sum of the series. It's very important to know that, all right? Do not tell me that the series converges to 1. It doesn't. We don't know what it converges to. We just know it converges. So, since 3 conditions hold, and integral 1 to infinity 1 over x squared dx converges, the series summation 1 over n squared converges by integral test. We don't know what it converges to. We know it converges. We have seen, so far, we have seen that summation 1 to infinity of 1 over n diverges. We have seen summation 1 to infinity 1 over n squared converges. You can go on and calculate n cubed and n to the 4th and maybe n to the 5/2 and so on. You can put any exponent on n that you want. If you do many of those integrals, you will actually make a conjecture, and then those of you interested in mathematics can actually go and do the proof. The proof says that summation 1 over n to the p has 2 possibilities. P larger than 1, convergence. P less equal than 1, divergence. And this gets the pink box, and it's called P series. So you see that the harmonic series are a part of this. Each problem can be proved by integral test, right? Each problem can be proved by integral test. So when you have a situation 1 over n to the p, this p for harmonic series is 1. We just did 1 over n squared, where p is 2. So if p is larger than 1, the series converges. If p is less than 1 or equal to 1, right, which is harmonic series, it diverges. This particular test, right, it's very simple, just like geometric, right? You look at value and you know. So you either memorize it or you didn't. You can't make it up. So we know for geometric, right, if the numbers, if r is between -1 and 1, we have convergence. If r is outside of that range, it's going to be divergent. Same thing for p, it's either larger than 1 or less than 1. Now, this will be heavily used on Wednesday when we do comparison tests. So you absolutely must know this one to understand next class. You can't leave this to learn on a weekend, because you'll be completely lost on Wednesday. You need this for Wednesday. On Wednesday, we're going to take a look at comparison test, and you're going to have some n squared plus blah, 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 divided by n cubed plus blah, blah, blah. N squared, n cubed, what canceled quotient there is 1 over n. You compare it to 1 over n, you're looking for divergence. So you need this. You need this for Wednesday. Integral test, right? If you have to postpone something for a weekend to study, integral test is the one, right, to work off. But I need you to know this on Wednesday, so you can finish off the chapter. And those are the 3 tests, guys, that we learned today. Now, I have to get something before the class is over in 5 minutes, right?
Yeah.
I have to get something that I forgot in my office, and then we'll... oh, actually, let me just put one example over here. So summation of n to the negative 3/2 from 1 to infinity. Where's the infinity over here? So what's happening here? You will use algebra to rewrite this as 1 to infinity, 1 over n to the 3/2, and then you will say p equals 3/2 larger than 1, convergence, done, right? So again, these problems are extremely quick, You just memorize the theorem, and then you use your eyes and you look at it and you know. 5 seconds, that's it. All right, bye stream, and I'll be